When multiple UASs share the same airspace, their relative geometry evolves continuously. A detect and avoid is the physical foundation for autonomous airspace situational awareness and the prerequisite for unmanned aircraft to become intelligent low-altitude agents. The onboard sensor is the critical entry point for DAA. It builds the traffic state vector in real time with an interior azimuth, elevation, range, and closure rate. Only when the onboard mission computer resolves this vector with millisecond latency and commands resolution maneuvers through the flight control link does the UAS achieve autonomous decision-making. ARCGine's proprietary fill sphere collision avoidance sensor delivers complete spherical coverage entirely on board. Independent of ground infrastructure, it constructs an omnidirectional traffic picture directly in the ownship body frame, enabling the UAS to independently perceive the kinematic state of intruding traffic. To validate full sphere collision avoidance, we designed a dual-star system dynamic resonance experiment. Two UAS fly in orthogonal elliptical orbits with major and minor axes of 20 and 8 meters. Over 7 minutes, they sweep through each other's complete spherical coordinate frames in dynamic resonance thrusts may emerge from any azimuth or elevation, constituting the most rigorous physical stress test of spherical sensing. Now, observe this physical verification. Two unmanned aircraft fly in sustained dynamic resonance along orthogonal trajectories. Every intersection represents a potential near midair collision event. Every close approach samples a new bearing and elevation angle in the other's spherical coordinate frame. Conflict detected. The onboard spherical sensor instantaneously locks the intruder's relative bearing, elevation, and altitude with millisecond-level precision. Intruder above horizontal resolution. Simultaneous climb. Intruder below horizontal resolution. Simultaneous descent. The two systems executed 95 successful avoidance maneuvers within 7 minutes, with every threat detected, resolved, and evaded in real time. This is not a pre-programmed flight demonstration. No ground control station intervention. No manual remote pilot correction. Only the closed loop of onboard spherical sensor, mission computer, and flight control system operating fully autonomously without any external command or navigation aid. The experiment succeeded. The significance of the dual-star resonance experiment is this. It proves that in real multi-aircraft traffic scenarios, an onboard full-sphere sensing system closes the loop of omnidirectional detection, conflict resolution, and dynamic response with millisecond-level latency.